Section 3.2 is titled Addition and Subtraction of Whole Numbers. And what we're going to look at in this section is some of the ideas behind addition and subtraction. Okay, so are we going to add and subtract? Yeah, we're going to add and subtract. But we're also going to look at sort of the premise behind that. So to start with, addition of whole numbers. Let A and B be two disjoint finite sets. We've talked about sets, right? Yes. Disjoint means they have nothing in common, and then finite means they actually have a numerical value you can associate with them. If n of A equals A, and n of B equals B, then A plus B is the number of items in the union of A and B. We call A and B the add-ins, and we call A plus B the sum. Right, so the idea is that if you took my family that lives in my house plus my sister's family that lives in her house, those are disjoint sets, and we just put this all in the same room and you just counted all of us together, that would be the same thing as counting each of us separately and adding those two numbers together. But it matters that the sets are disjoint, right? Okay, so if you have the one child that goes back and forth between mom and dad's, this doesn't work. You guys with me? So the idea of them being disjoint is really important here. All right, an example to show why the definition of addition must be disjoint. So we're going to do an example with just some numbers and so forth, but you could actually write out something like I just described. You know, you've got this child and he goes back and forth between mom and dad's. That would be fine. I think it's a little bit more clear if we just used numerical values. And some of you are working through a test correction problem that's causing you some grief about whether or not you can distribute some things. So this would be a really good model to think about how you would go about proving or disproving that that statement works. Okay, so if you're looking at that problem on the test, I don't know if it's like, Kerrigan, what number problem is that, like 9 or 10 or something? Think about how I'm setting this problem up, and that might help guide you in how to set that problem up for it to make sense. All right, so we're going to let A and B be these two sets, and it says we're supposed to show why they have to be disjoint, which means that we're going to make them not disjoint and show that the argument doesn't work. So not disjoint means that they're going to have something in common. So I'm going to let A be 1, 2, 3, and 4. And I'm going to let B be 3, 4, 5, 6, and 7. These sets are not disjoint, right? Why not? Have a 3 and a 4 in common. Okay?
Disjoint are the ones that don't have anything in common.
Disjoint are the ones that don't have anything in common. Okay, so if I were to erase the 3 and the 4 from one of them, these would then become disjoint. But right now, they're not disjoint. So what I want to show you is that if you count now, whoops, I meant to do A first. What are the number of items in set A? 4, right? N of A means count the number of items in the set. N of B, the cardinality, what are the number of items in set B? There are 5. And if you actually added N of A plus N of B together, you would then get 9. Okay, the problem is that if we did it in the other order, that is, if we found the union, what is the union of A and B here?
7. Oh, sorry. 1, 2, 3, 4.
Good. It's all the numbers from 1 up till 7. And if we looked at the number of items in A union B, then we would get 7. And you notice that these two things are not equal, right? Counting the items in the union is not the same as counting the items in the individual sets and adding together. It's exactly off by 2. Why? Yeah, we repeated those numbers, right? Those are the 2 overlap spots. Those are the problems that are causing it to be disjoint. So we end up not having this actually work. Okay, so it does matter that the items are disjoint to be able to use this argument. All right, there are two of these. There are 2 models for addition. The first model is called the set model.
Sorry.
Yes, Leah?
Would that mean that the one on the test is not true, that it's not equal?
That's what you have to decide. But it's much the same in terms of how you're going to count things, right? Because this question is very similar to the one on the test, isn't it? Yeah. So give it a try. Create 2 sets and work with them to see whether or not this actually ends up working for you. Okay? Okay, 2 models for addition. The first model is called the set model. It's usually used for something that's a whole object. So here's an example. Liz has 3 blue crayons and 2 red crayons. If she combines all of the crayons, how many crayons does she have? Okay, 5 crayons. And there's, this is a set model. The concrete version of doing this is that you could actually physically use crayons. And even if you don't have the crayons, we have wonderful capabilities right here that are going to allow me to draw something like a crayon. Let me see here. Okay, we have 2 red. Those are my 2 red crayons. And we had, 3 blue?
Yeah, 3 blue.
3 blue. So there are the crayons all drawn together. And then we could actually physically count them up and we would get 5 crayons. So your tactile learners could do this, right? Tactile means you have to touch things, right? Okay, so this is the set model. Again, the idea is that it's whole objects. So we don't talk about halves of crayons. Right? A crayon just is a crayon, no matter how big it is. That's when we usually describe it. However, there are some things that don't work quite like that. The number line or the measurement model is typically used for objects that can be partitioned. So usually measured lengths of things, like this one. Joe has 4 feet of wood and 3 feet of aluminum. How many feet of building material does Joe have? Okay, we're not actually counting the pieces of equipment he has, we're counting the lengths of the equipment that he has. It's still whole numbers, right? We're only working with whole numbers in this particular chapter, but there's something uniquely different about this than the other problem. Do you guys see it? I mean, do you feel like this one seems different with those feet?
Different things, you can't really combine.
That's part of it, it's they're different things, but it isn't so much that they're different things, it's that they have lengths of things. There's a length of them being talked about. See, it doesn't really make sense. I mean, you could talk about the half of a crayon, but honestly, when some kid has half of a crayon, do you call it half of a crayon? No, you still call it a crayon, right? It's still a crayon. But if you have a foot of aluminum and compare that to a half a foot of aluminum, that is definitely different, right? It's being measured in a different way. So in terms of drawing this one, what we're going to do is we're going to actually draw a number line out, because this is the number line or the measurement model, and we're going to sort of hash mark out these values. So here's my 0. I didn't quite get my line long enough, but we'll make it there. Okay? And we started out with 0, and it says we have 4 feet of wood. So if we're measuring this out, we would actually measure out the 4 feet of wood. And just because I can, I'm going to also put some color to this, because I can. Here's my 4 feet of wood. I think that's 4. Maybe I should make it just a little bit thinner so I can see it. That's better. There's my 4 feet of wood. There's my 4 feet. And the other one is supposed to be 3 feet of aluminum. So there's the 3 feet of aluminum. You're measuring them. You're not counting them. Right? Measuring instead of counting. And then the answer would be what? Yeah, it'd be how far out we went. This would be 7 feet of material. All right, less than. For any whole numbers a and b, we would say that a is less than b, written a, we've got that less than symbol, b, if and only if there exists a natural number k such that a plus k equals b. All right, so if I were to have one of you who is shorter or taller than me come up here, we could talk about whether I'm shorter or taller, whether my height is less than or greater than you, based on if I could add a heel on that would make us the same height, right? If I can add a 2-inch heel on my feet and then I'm the same height as you, then I have a height that's less than you. And you can do this with the numbers that they're talking about here. The reason that 5 is less than 7 is because there is a number that I can put right here that makes these equal. We know it's the number 2, of course, but that's what it means to be less than. It means that there's a number I can add to it to make them equal. Now, using this is a definition of less than. What we're going to do next is we're going to give the definition of less than using addition. I've added something to one piece. Our example next is going to be giving the same definition of less than, but it's going to be using that definition and writing it as a subtraction equation instead of an addition equation. So the equations, or the definition is going to look much the same. It's going to say something like this. We're going to just mirror exactly what the other one said. For any whole numbers, A and B, A is less than B, written at A less than B like this. If and only if there exists a natural number, remember those are our counting numbers starting at 1, a natural number k such that, okay, so I hope at this point you felt like that you're writing down exactly what was written on the definition before. Did you? Yeah, absolutely, perfectly, exactly the same as the previous definition. The part where they vary or they differ comes with the next part. The directions in this problem say that they want us to set this up using subtraction instead of using addition, right? So the previous one said where A plus K equals B. How could I write it with the A, the K, and the B so that it's a subtraction equation instead? A equals B minus K. So this doesn't work as well as my adding my heels kind of question, but let's just say that one of you came in today and you had heels on. Okay, we're normally the same height, but you have heels on today, and if you were to take off those 2-inch heels, then we would actually be equal in height. I mean, I don't want to cut your legs off because that sounds like awful, but we could take off your heels and that'd be okay, right? You're removing a portion from a piece of it so that the two values are equal now instead. Okay, another definition of less than. When you get to your homework for this section, you're going to do the same kind of thing here, except you're going to do it for greater than. And they'll tell you whether to use an addition or subtraction equation to do greater than. It's going to feel almost like you're writing the same stuff. Okay, very, very similar. But you're just doing it for the greater than value instead of for the less than value. All right, we have 4 properties of whole number addition that we want to talk about. The first property is by far the one that causes people the most grief. Okay, so let's get them written down first on all 4 of them, and we'll go back and then we'll talk about all 4 of them. The first one is the closure property. It says if A and B are whole numbers, then A plus B is the whole number. Okay, so if you have 5 plus 7, it's going to be a whole number because 5 and 7 were whole numbers to start with. No matter what 2 whole numbers you pick, if you add them together, you get a whole number. The second one is the commutative property. The commutative property said is that the order of addition with whole numbers doesn't matter. 5 plus 7 is equal to 7 plus 5. There's nothing special about the ordering when we do addition with whole numbers. The third one is the associative property. The associative property says if we have 3 numbers that we're adding together, then it doesn't matter which 2 we add together first. So if you have A plus B plus C, you can add A and B together first, or you could add the B and the C together. The order of those doesn't matter. And the word that I like to use with associative is that we're associating different values together. That's what those parentheses do. When you talk about associating with a certain group of people, you are grouping yourself with them. And that's what these are too. These are grouped together. And then the last one is the identity property, and it says there is a unique whole number, 0. It's the additive identity because for any whole number A plus 0 equals 0 plus A equals A. It's the only value for which that works. A plus 0 equals 0 plus A equals A. You missed them from the previous slide. I'm about to go back to it. Okay, does everybody have this one? We're going to flip back and forth between these slides a couple of times, but okay, so let's talk about closure, because you might look at that and you'd say, well, duh. Whole number plus a whole number is a whole number. So what? Well, that's actually quite unique. Not all number systems work that way. If you take a fraction plus a fraction, do you get always a legitimate fraction-looking value? No. Sometimes it ends up being a whole number when you're done, right? If you take a positive, if you take, I don't want to talk about multiplication just yet. We'll do multiplication next time. If you take,
If you like odd plus odd, you would minus.
right, that's a great example. If you do odd numbers, if you take an odd number plus an odd number, do you always get an odd number? No, in fact, you never get an odd number. But if you did even numbers, it would work, right? Even number plus an even number is always an even number. So this doesn't always work with every number system, but it does work with whole numbers. So part of when you do your homework, they're going to take you outside of your whole number properties and talk about other numbers. They're going to do things like consider multiples of 3. Are those closed? Consider the set that has 2 and 5 in it. Is it closed? So here's the way that you can talk about closed systems. We've got a door on the room, right? And right now this door is closed. All right, so whatever number system you're working with, all those numbers are in the room with us right now. All right? So in this one, we're talking about whole numbers. So the whole numbers are all floating around in the air somewhere. The idea of it being closed is you can take any two whole numbers out of the air, you can combine them with the operation you're talking about, in this case it's addition, and you will get another number that's floating around in the air in here. You do not need to open the door. It's all here. Everything you need is here.
So it's like if the answer is a part of the problem?
If the answer is a part of the set that you're working with. So if you're working with whole numbers and you add two whole numbers together, the answer is a whole number.
It doesn't have to be that one, it's like one in that.
Right. It has to be something else that's in that type of number. So we're going to use Emily's example where she said odd numbers. So if you had all the odd numbers floating around in here and you took two odd numbers from the room and you added them together, what happens when you add two odd numbers together? The result's always even, doesn't it? Think about it. Can you think of examples? So if you were to take two odd numbers and add them together, the answer would not be in this room because the only things in this room are odd numbers. So you'd have to open the door where the other numbers are, waiting in the hallway. It would not be closed because the answer's not in the room with us. Okay? Commutative, again, you might say, commutative, of course this always works. What's the deal? Well, it works because it's addition and it's whole numbers. Let's say for a moment that this were subtraction, which we'll talk about more at the end of this particular lesson in 3.2. If you do subtraction, does this work?
No.
No. 5 minus 3 is not 3 minus 5. Right?
Right.
There's something unique about addition that makes this work. If you do associative, same thing. This is unique to the whole numbers with addition property. If you work with this with subtraction, again, we'll learn this next class period, it's not going to work. And then the unique property or the additive identity property is a unique value. 0 is the only one that works. Now, I often will ask a question, I think it's in your homework is where it shows up, and it asks why is, and it gives you two values. Why is this value and this value additive inverses? Or additive identity. Why is it an additive identity? Well, if it's an additive identity, it means that when you add it to something, it doesn't change it. right? Additive identities are super useful when you're solving equations. You guys have used them forever, right? If you add something to both sides of the equation, it doesn't change the equation. You've added the identity in some fashion. You do it in a funny way. You don't really put in the number 0, but you do. You put a 5 on one side and a 5 on the other side. That's the same thing. If Ashley and I are standing up here and we both put on 2-inch heels, we haven't changed how much our heights differ, right? Because we've both put on the 2-inch heels. That's an additive identity. It hasn't changed the value of what's going on. All right, so what we're going to do next is we're going to identify which property is being used in these 4 examples. So I'd like for you to write down commutative, closure, associative, or identity, which of the 4 it is. So jot those down, and then we're going to make sure that yours and your partner's matches, and then that everybody's matches. So fill in what you think these 4 are, and then share with a neighbor. Share and compare.
Is distributive not one of these properties?
Distributive requires the use of 2 operations, multiplication and addition. And right now we're only talking about addition. So we will see the distributive property, but it won't be till section 3.3.
I don't do it. Because you can switch the numbers and they're still going to be equal either way. And the second one I wasn't quite sure, but I thought it might be additive identity. Because it's like talking about with the 0, because 0 is not, you're going to add 0, it's still going to be the same, you're going to get it on the other side. And then on C, I'm going to commutative, because again, you're switching those numbers. And the last one is associative, because you're just switching the name to 0.
And then for D, I put associative.
All right. I think you all communicated with someone nearby. It looked like it mostly. What did you have on the first one? What property is this? Commutative property, that's right. So this one is commutative. What's the second property? That's the identity. The identity has the property that if you add it to it, nothing changes. So if 6 plus 3 plus 0 is equal to 6 plus 3, that's the identity property. C was meant to throw you off a little bit. Did anybody get thrown off a little bit? Yeah? What is C? It's actually commutative. In order for this one to have been associative, you'd have to have the parentheses not have the same thing inside of them. So if you take a look at the 2 sets of parentheses here, this set of parentheses has 6 plus 8, and this set also has the 6 plus 8, just in a different order, right? And when we change the order of something, that's actually the commutative property at work. How about D? Associative. That is associative. We've actually changed what is inside the parentheses. Let me make mention right here that this is the additive identity. And please write it on there for you as well. Because we will have another identity later, and it will not be 0, since it will not be the additive identity, and we will have to clarify which of the identities it is. Okay? All right, we will pick up next time with some basic addition and subtraction strategies, and we will talk about subtraction models as well. Have a great couple days.